Okay. So hello everyone. Welcome. Welcome to this new seminar from the IAA in Granada. So today we have the pleasure to have with us Michu from the Institut d'Astrophysique de Paris in France. She will be talking about off-center black holes in red central galaxies. So Aline Chu defended her PhD just a few months ago in December 2022 at the IAA in Paris under the supervision of Isabel Marquez and Florence Dupré. And she's still working at IAP, but now she will be moving at the end of the year to Stockholm, to Sweden, to work in the Oscar Klein Center to work on LSTD. So she's an expert in galaxy clusters, and in particular in the brightest galaxies of galaxy cluster, BCGs. So her thesis has the title of Evolution of the Physical Properties of the Brightest Central Galaxies of Galaxy Clusters, and then she studied how the physical properties of the cluster galaxies evolve with time, and use these results to constrain their formation. She also studied the brightest galaxies of fossil groups, which are groups with an exceptionally bright central galaxy. Her work is mostly based on observations and data reductions and analysis, but she also tackled red galaxies and their supermassive black holes in relation. And this is in fact the subject of her seminar today, where she will be talking about the central black hole peaks from the central regions that emerge out from the dynamical interest that BCGs experience through their history. So now the floor is to you, Aline.
So, hello everyone. Thank you for the introduction and for having me here. So I'm a visitor at arrived Wednesday, and I'll be staying until Monday noon. So if you want to come discuss with me, we can Instagram. I'll be very happy to present. So it is a pleasure for me to present you the last work I have done, which is a paper I have done not with Isabel, but with two other collaborators in Paris, so it's Pierre Boldrin and Joseph. And I'm going to present you the paper that we have done, which is on off-center supermassive black holes in bright central galaxies. So this paper is currently in production in NRAS, but you can find it on the archive. In the meantime, it's going to be published very soon. So before I get into the core of the subject, I would like to introduce and define each terms of the presentation title just as an introduction and just to lay down the base. Okay, this one. Okay. So let me. Can I want this? Okay, I shouldn't have to write that. Okay, so does it bother you?
Maybe you can move it to the other screen.
Or click in the. Okay, okay. So let me start with a very general introduction and talk a little more about naming expertise, which, as I said, is not really about supermassive black holes, but rather on galaxy clusters and more specifically on their central galaxies. So, as you may know, galaxy clusters are the most massive and the largest structures which are known today in the universe. And those are extended structures of 10 to the 14, 10 to the 15 solar masses. Sizes which range between 1 or 2 megaparsecs, and they're also filled with hot gas. So these clusters are filled with are composed of 100 to 700 galaxies, which are bound by gravity, but there also exist smaller systems of less than 100 galaxies, which are called groups of galaxies. So by definition, clusters are galaxies and environments, which means that collision interaction between galaxies and galaxy mergers must be more frequent than in the field. This is why, if you look at this image of the cluster on the left-hand side, clusters are usually described as an over density of red galaxies, which are formed by the merging of two galaxies of similar masses. And they have very, very few spark blue galaxies, which you can mainly use in the field, where galaxy mergers are much less frequent. So this is why galaxy clusters are the perfect laboratory to study how environmental processes can affect the formation and the evolution of galaxies. So if you have to remember two words from this slide, it's galaxy mergers. Okay. So galaxy clusters are also often referred to as knots in the cosmic web. So they are located at the intersection of the cosmic filaments, which bring them matter such as galaxies or smaller systems, such as smaller groups or smaller groups of clusters of galaxies. And all this ordinary matter falls to the bottom of the cluster potential well, which is also commonly the center of the cluster. So here we can see what is happening exactly at the center of the cluster in the simulation from the Eagle project. So as you can see, as more and more matter sink to the bottom of the, let me remove the line. Okay, as more and more matter sink to the bottom of the cluster-wide cluster potential, there is a supermassive galaxy that is forming and interprets all this material and it's merging with other smaller galaxies. So this galaxy is growing this time as more and more matter is brought by the cosmic filaments. And eventually this galaxy often ends up being the most massive of the brightest galaxy of the cluster, and it is referred to as the brightest galaxy, like the brightest cluster galaxy, or the BCG, to make it short. So brightest cluster galaxies are exceptionally bright objects, which by definition are the brightest galaxies in their clusters. And they are usually defined as supermassive galaxies, which lie at the center of the host clusters. So on a cosmological point of view, as I said before, galaxy clusters are the perfect laboratories to study how environmental processes can affect the formation of galaxies. And BCGs along the same lines can infer how the processes can affect the growth or the dynamics of galaxies. So because of their central locations, BCGs are more likely to experience mergers during their lifetimes, even more so than just any other galaxies in the same cluster. So they thus represent the final products of theoretical merging at the galactic scale. So this is why these objects are very interesting to study. And so BCGs are mostly early type passive galaxies with quench star formation. And this absence of star formation in these massive galaxies can be due to many factors. So you have, of course, galaxy mergers, during which you can have gas that gets consumed to produce large spaces that will have happened many long ago. And during this process, you can also have gas that gets ejected, which gives the resulting galaxy with little to no gas. So you have many other processes that are to take into account, but one of them that is believed to play a huge role in the friendship of galaxies and the development of elliptical galaxies is supermassive black holes. So all massive galaxies, including BCGs, are believed to, so BCGs are the most massive of galaxies. They are believed to host a supermassive black hole in the center, which is believed to play a huge role in the shaping of these galaxies, and more specifically in the quenching of the formation in ejected galaxies. So more precisely, black hole feedback, which is produced by the release of energy into the intercluster medium after the accretion of matter by the supermassive black hole, is believed to hit the surrounding gas, preventing it from cooling down and thus to collapse into stars. So in this way, it regulates the star formation at the center of this massive galaxy. So it was shown in simulations that only take into account gravitational collapse as the main clustering process to form stars, led to star formation rates in this massive galaxy that are way too high compared to the star formation rate that we observe, that we measure from observations. So now we have supermassive black hole feedback that has been implemented in many simulations in order to balance this out and to reach star formation rates that are much closer to the star formation we measure from observations. So just I think that the simulation that only take into account gravitational collapse finds star formation rate of the order of 1,000 solar massive per year, whereas actual BCGs have particularly non-existent star formation going on. So this huge discrepancy between the simulations and observations is also known as a Colin problem. So now that we have the base laid out, we can get into the core of the subject. So we are going to study, we aim to study the impact of galaxy mergers on the supermassive black hole of the BCG. So this study was first motivated by observations which show that, contrary to what is commonly thought, BCGs can be displaced by spherical parsecs from the center of the X-ray emission of their host clusters. So the X-ray emission usually traces the potential of the cluster. So this is one of the results we have from of my first paper with Isabel from Xue 2021, in which we compare the optical position of the BCGs which were observed with the Hubble Space Telescope, and we compare this position with the center of the X-ray emission, which were obtained with the Chandra telescope. And as you can see here in this plot on the top right, so we find that most BCGs are relatively close to the center of the X-ray emission of the cluster, but still we have a significant fraction that is displaced by more than a dozen or even 100 kiloparsec from the X-ray emission of the cluster. So we can reach even 200 kiloparsec. This is really, really huge. And so we wondered if this offset could be a sign of an center supermassive black hole in the cluster. So again, BCG, because they live in very high density environments and because of their central rotation, they are more likely to experience galactic mergers in their lifetimes. And we suspected that some of these mergers may be able to kick away the black hole from its central position. So why that question interesting? So if you remember the cooling component I presented to you the last slide, which needs AGN feedback to regulate the star formation in massive galaxies, we actually have some studies such as Brightest 2020, which find that black hole feedback, if this black hole is off-centered, could become inefficient. So this was demonstrated to be the case for dark galaxies, but we also have since the 2018 that suggests that it may also be the case for more massive galaxies. So if this is true, then we have a huge problem in the simulation that need AGN feedback to quench star formation in elliptical galaxies. So this is what we looked for. So we tried to study the impact of galaxy mergers on the supermassive black hole of the BCG. And for that, we used 370 galaxy clusters from the illustrious TNG 300 simulation. So illustrious TNG is a large cosmological hydrodynamical simulation for galaxy formation. And here we used the largest box of the size of 300 megaparsec, which enabled us to collect a larger sample of galactic cluster and to study the clustering of the systems. So here the cluster were detected by band 2018 and have a median mass of 508.8 × 10^13 solar masses. So the question we aim to answer is, can galaxy mergers affect the supermassive black hole, and if so, how much? So let me present the method that we used to answer this question. So first, we try to reconstruct the merger history of the BCGs since Project 2, so in the last 10 billion years in the illustrious simulation. So, and we try to identify all the main satellites the BCG merged with in the last 10 billion years. So here you have an example of a merger tree from illustrious. So we identify the BCG as the most massive subhalo in halos. In other simpler physical terms, it's the most massive galaxy in its host galaxy at all time steps. So here you have the size of the dots is relative to the mass of the galaxy, so bigger dots correspond to more massive galaxies, and you can follow the BCG by this line here with the bigger dots, and identify all the satellites with which it merged and retrieve the times at which this merger happened. So the mergers, you can identify them as well where the dotted lines are and where there is a bifurcation in the diagram. So yes, and another just comment is the BCG is always more massive than the satellite. So the total mass of the BCG is always bigger than the total mass of the satellite, but the two can still have comparable masses. Okay. So then for each satellite, once we have identified them, we can compute their orbits in the potential of the BCG. So for this, we use orbital integration methods, and we use GAPI for that. So GAPI is just a Python package for galactic dynamics calculations. So here I just want to preface this by saying that we do not take the orbits of the satellites directly from the simulation. So GAPI is completely independent from industries. So technically, if you wanted to do it in a very simple way and obtain the orbits of the satellite, you could just take the simulation, retrieve the position at all time steps, and then you have the orbits. Doing so, you are quite limited by the limits of the simulation. You don't have that good of time resolution or spatial resolution. So doing so ourselves, we can not only have better time resolution, but we significantly increase the spatial resolution of the orbital calculation. So this allows us to determine precisely how close to the BCG center the satellite is going, and so if it can possibly affect the central region of the BCG where the black hole is supposed to be. So doing so enables us to go beyond the limits and the constraints of the simulation, but not only, because so in the simulations you have some processes which are still badly treated, for example, dynamical friction. And here, by doing the whole calculation ourselves, we can introduce, for example, the Supermassive dynamical friction, which returns even more precise orbits. So having said that, we still use illustrates to get initial parameters for the satellites and the BCG. So we retrieve the three-dimensional velocities, position, as well as the dark matter, gas, and stellar masses of the BCG and the satellites. And with these properties, we can compute the orbit of the satellite, which is falling in the potential of the BCG, which we model here by a Helmquist profile for the dark matter distribution, and the Plummer profile for the stellar distribution. And then it has dynamical friction, the Supermassive dynamical friction, which makes it lose energy and go back to its central position. So here the satellite is described as a point mass, which is following the potential of the BCG, which I just defined, and which suffers dynamical friction that takes into account its size. So in the end, you get this, for example, it's the orbital radius of the satellite relative to the center of the BCG. So from this, from the orbits of the satellites, we can determine for each of these satellites which has the potential to affect the supermassive black hole. So the satellite needs to satisfy two conditions to keep away the black hole. So the first one, we need a radial merger. And by that I mean that the satellites must have a radial orbit as it is falling in the potential of the BCG. And second, the satellite must be massive enough. So for the first one, this means that we need the satellite to pass close enough to the center of the BCG, where the black hole is, so that the black hole will be able to feel its influence. So in mathematical terms, this happens when the distance between the BCG and the satellite, or the distance between the satellite and the black hole, because the black hole is originally at the center of the BCG, is smaller than the half mass radius of the satellite. Another thing to know about this is that we neglect the mass loss and the mass transfer of galaxies during the process, because otherwise we're going to have a change of masses at all times. It's going to be way too complicated. So we neglect all this mass transfer. So this means that this condition, in order to be true, is to be true on the satellite's first passage in the potential of the BCG. So in other words, the satellite needs to have a radial orbit. Then for the second condition, which is on the mass of the satellite, we need the satellite to be massive enough so that it will be able to give enough, to transfer enough energy to the black hole to keep the black hole away. So this is translated by the total mass of the satellite needs to be bigger than the total mass of the BCG. which is enclosed in a radius d, which is the distance between the BCG and the satellite. It is the same one as this one. And so for each of the satellites, we check if it meets these two criteria, and then we retrieve a list of satellites that do. And finally, we can then compute the orbit of the supermassive black hole and the potential of the BCGs through several mergers in the last 10 billion years. So the supermassive black hole is described as a point mass, which is in the potential of the BCG, and which suffers then dynamical friction in its environment. So the supermassive black hole is originally on a circular orbit at 100 times the Schwarzschild radius of the black hole, and we fix its mass also out the calculation to 0.06 times the stellar mass of the BCG. The stellar mass of the BCG being the one we get in the simulation at the time the first merger that displays the black hole happened. So basically, after a merger, so as a merger happens, the satellite is going to transfer energy to the black hole, so the black hole is going to get more energetic. It's going to be kicked, so its velocity changes, and its orbit is going to become more eccentric. So it gets kicked, and then because of dynamical friction, it goes back to its central position. And then then as the next merger happens, we have two possible scenarios. We have the first one in which the black hole gets kicked again by the satellite. And the second one is there is a satellite that has already kicked the black hole away and doesn't have time yet to go back to its central position. So the next satellite does not manage to kick it in. It does not affect the central black hole. And this is because chances of encounter between the satellite and the black hole are much lower outside the central region of the BCG. And the two conditions that I showed you in step 3 are much more difficult to fulfill, especially the second condition, the mass of the satellite, are much more difficult to fulfill the further away the black hole is from the center of the BCG. So we wait for the black hole to go back to its central position in order to be able to be kicked again. And that's basically how we trace the dynamical history of the supermassive black hole since redshift 2 to redshift 0. So I just want to emphasize again that we do not take the orbits and the orbits of the satellites and the black hole directly from the simulation. We do the whole calculation again ourselves. And it takes the simulation to get the initial parameters like the position, velocity, or mass of the black hole, and not the black, yes, of the black hole, satellite, and BCGs. Galaxies are otherwise completely independent. So this allows us not only to have better time and spatial resolution, but also to implement other processes like dynamical friction, which should not be neglected and needs to be taken into account. So this is something I already said before, but I just want to point out why this is particularly important. So dynamical friction is the process that allows the supermassive black hole to lose energy as it interacts with the environment and to go back to the bottom of the BCG potential well. And because dynamical friction is still very badly predicted in the simulations, some problems can arise and can arise in the simulations that try to reproduce the formation of galaxies. And this is, for example, the case for the electricity in the simulation. So AGN feedback in the simulation, so the inject energy that has to produce the energy needed to quench the formation. AGN feedback is in the simulation greatly relies on the central position of the black hole in order to act efficiently and thus super rapidly, and then to have efficient feedback to quench the star formation, to hit the gas and quench the star formation. So an easy way to get rid of the problem of dynamical friction in the simulation is just to either fix or position the black hole to the center of the potential well. So anything could happen. You could have a huge major merger of clusters winds, whatever, they will fix it at the same position, which is completely non-physical. So here we can overcome this by computing the orbit of the black hole ourselves, and I think this is one of the points that makes this study particularly interesting. So this is what illustrates, for example, it always fixes the position at each center the black hole to the center of the center. So here, let me show you an illustration, so just so you can visualize better what is happening. So you have a satellite on the top left in orange that is going to pull in the potential of the BCG. It's going to eject the black hole represented here by the little black dot. And then the two are going to suffer dynamical friction and are going to go back to the center of the BCG. So here we go, it gets kicked and then they go back. So let me remind you of the two conditions that need to be met to kick away the black hole. So the activax needs to have a radial orbit and it needs to be massive enough. So as you can see, as you can see, it happens when the satellite passes by very close to the black hole, when the distance is less than the half mass radius of the satellite, which is represented by the orange circle. And of course, the satellite is massive enough to attribute to the mass of the BCG. So in that case, the black hole went to a distance of about 11 kiloparsecs. So this is the resulting orbit of the black hole relatively to the center of the BCG through several mergers in spreadsheet 2. So in that case, you have 4 satellites which manage to kick away the black hole from its central position. So this video illustrates the first merger that happened. So as you can see here, we have 4 satellites, which is represented by a peak because the satellites give it a peak, and then they go down because of dynamical friction. So the offsets can be quite significant, and they vary greatly because the offset depends on the mass and the velocity of the black hole, BCG, and satellite. So the first one here managed to kick away the black hole to 1,000 kiloparsec, but then you have the second one that displays the black hole by 140 kiloparsec. So it's very big. And then you have the third one up to 80 kiloparsec, and finally the last one, which went to 100 kiloparsec. And what's interesting to note also in this diagram is that the last merger actually happened quite recently. So it happened in the less than 2 billion years ago. And if you can see that it didn't have time to go back to its central position yet. So even at redshift 0, it is quite off center because it is still at 20 kiloparsec from the center of the BCG. Okay, so now let's look at the results we get considering all the 370 clusters we have in our sample. So on the left-hand side, we have the satellite stellar mass as a function of the BCG stellar mass. So here you have all the satellites with all the cluster between redshift 2 and redshift 0. And we distinguish two populations. So in green, you have the satellites that did manage to kick the black hole away, and in orange, you have the satellites that did not manage to affect the central black hole. So as you can see, not all satellites manage to kick away the black hole. Actually, they are very rare because they only consist of 3% of the total merger population. And out of the 370 clusters, we have 170 clusters which have their black hole kicked away at least once since the last 10 billion years. So it's about half of them. And if you look at this diagram again, you can see that most of the black holes that have been kicked to their central position have been hit by satellites that tend to be quite massive. So they have a stellar mass ratio, which is at most of 100 with the BCG stellar mass. So here you have the dotted line, which represents a fixed mass ratio of 100. Most of the green points are above that line, but you can also see that there is a huge cloud of points, of orange points, so massive satellites that did not affect the black hole. And we have two explanations to explain this. So the first explanation, which is the main one, and which concerns 95% of the satellites above that line, are massive satellites that do not have a radial orbit. So they did not go by they did not pass by the center of the BCG, so they did not affect the black hole that is supposed to be there. And for the remaining 5%, those are massive satellites that do have a radial orbit, but at that time, at the time of the merger, the black hole was still off center, so the two did not meet and they could not be affected. Then on the right-hand side, you have the black hole offset as a function of the black hole mass. So here you have in orange, the offset that is measured at redshift 0, and in purple you have the maximum offset that has been measured since redshift 2. So here you look at the orange points, you can see that more massive black holes tend to exhibit larger offsets than less massive ones. So the trend is not very strong, but it is still significant. And it actually makes sense in a physical sense, because in the hierarchical model, structure formation model, we have more massive galaxies that tend to be less dense than less massive ones in their centers. So if it is less dense, it means that dynamical friction that acts on the black hole is going to be weaker, and so the black hole takes more time to lose energy and then to go back to its central position. So that's why you observe more significant offsets in more massive black holes than in less massive ones. And then if you look at the purple ones, it shows you that you have offsets that can be of the order of 1,000 parsec to hundreds of kiloparsecs. Okay. So here we have other results. So here we only consider the black holes that have been kicked away at this point since redshift 2. So it's the 170 clusters. So this is the cumulative distribution of the extent of the black hole offset, depending on, I'm sorry, you have something in the way. Depending on, so the yellow curve represents the offset at redshift 0, and the purple one represents the offset, the maximum offset that has been measured since redshift 2. So if you look at the yellow curve, it tells you that 60% of supermassive black holes are still off center by at least 100 parsec at redshift 0. So this is a cumulative distribution, so I know it can be very difficult to read, so I'm going to break it down for you. So you are looking at all the black holes that are offset by at least 100 parsecs. You are looking at this side of the plot. And it tells you that it's 1 minus 0.4, which gives you 60%. And then you have the purple one, which shows that offsets rank between a few parsec to 100 kiloparsec, with most of them being on the order of 100 kiloparsec. Okay, then we have we evaluate the duration of the black hole offset. So depending at its distance from the center of the BCG. So here in green you have the duration of the black hole offset. A distance is bigger than 10 parsec. In yellow, a distance is bigger than 100 parsec, and in purple, a distance greater than kiloparsec. And if you look at the green curve, it tells you that you have about 85% of black holes that spend more than 6 billion years. The distance is bigger than 10 parsec. The yellow one shows you that you have 60% of supermassive black holes that spend more than 6 billion years, so it's like half of their lifetimes. A distance is bigger than 100 parsec, and then the purple one indicates that they spend about between 1 and 3 billion years at distances further than a kiloparsec from the center of the BCG. Okay, and finally, we show the cumulative distribution of the specific times at which the first kick, so the yellow one, the maximum kick in purple, and the last kick in green happened. So we have about 70% of supermassive black holes, which experience their first kick long ago, before redshift 1. But still, we have about 50% of them that experience their last kick very recently in the last 6 billion years. So this explains for all the black holes that have been injected in the time frame, they may not have had enough time to go back to their central position yet, and so they may still be off-center today. So all these results show you that supermassive black hole offsets are common in BCGs, and they may still be, they are likely to still be observed today. So what does it imply? We have two main consequences. First, gas clumps are mostly concentrated in the center of galaxies. So if the black hole has been off-center, then it means that it has been displaced to less dense environments. So the accretion is going to be less efficient. So it has been well established now that supermassive black holes provide the accretion of matter. So if it is off-centered, it has less matter to accrete. So its growth is more or less heightened. It is less efficient. And yes. And then along the same lines, because it is because the accretion is less efficient, it has less energy to release. So feedback also becomes less efficient. Then, because it is spending more than half of its lifetime outside the central region of the BCG, it also means that black hole-black mergers are also less likely. So the merger between the black hole of the BCG and the black hole of the satellite galaxy with which it is merging, it is also supposed to be hosting a black hole. So we suggest that galaxy mergers have a strong impact on the dynamics of supermassive black holes, on the dynamics that trains at the center of BCGs, and that the masses of black holes and the importance of AGN feedback may be very overestimated in the simulation that will produce the formation of galaxies. So if we take again the example of AGN feedback, we suggest that this agent feedback they want to reproduce may be too important, and they have to take into account more other processes that would hit the surrounding gas to quench the formation of the elliptical galaxies. So with this, I am done presenting this paper. So thank you very much. And if you have any questions.
Thank you, Aline. So now the seminar is open for questions, or here in the room, or also in Zoom. If someone has questions, please raise your hand.
Thank you, Aline. Super interesting work. I think you have said it, but I missed it. So how do you treat the galaxies that you shoot in your simulation as a point mass, or is it?
Yeah, it's point mass. So the satellite in the next will have to that point mass.
Okay.
Yeah. So the size is taken into account in the dynamical friction.
The size is being taken into account in dynamical friction, but you don't treat it like an extended.
No, because then it's become too complicated, and we have to.
Yeah, no, I guess it's important to calculate. And I mean the center of the BCG, you also treated
The BCG
as
has
fixed, or I mean, you would drag along not only the black hole, you would drag along mass of the BCG as well, wouldn't you?
So the black hole has a fixed mass because we
That's-
start from the hypothesis that if it is phase, then it's not going to go anymore.
Yeah.
So since relative 2 to relative 0, well, since the first measure to relative 0, we fix the mass of the black hole. So the mass of the BCG at the time the first measure happened. But the mass of the BCG changes with time. So we take the mass of the BCG from the simulation.
But when you kick it, you just the black hole moves, or do you also move the stars along? I mean, the entire
No,
core
just
of the
the black
BCG
hole.
would move. wouldn't
Yeah,
it?
it's just the black hole.
Okay.
Yeah, because it's
I
very.
know it must be massively complicated. Yeah, no, I completely agree.
Yeah.
I just wondered about what potential effects could be
Yeah.
there, but yeah, I guess it's
It's a very simplified version, but otherwise it's just too complicated.
More questions?
Continuing with the pencil operators, continuing with the question from Aina. I mean, yes, the black hole moves, but imagine if there is a relativity jet associated with the black hole, it will move.
I guess, yes.
Yes.
Yes, yes. It's just the first approach to everything.
Yeah.
And then we have to complexify the model.
I have a comment on your question. In fact, there have been radio AGN
Yes.
offsets detected in both galaxies.
Yes, I know.
So it's supposed that the kickoff has been taken place for those, and everything's not really,
Yeah.
black. So you see the radial emission from the black hole displaced with respect to the center of the
Yeah,
galaxy.
there are cases where you have also already captivity. In fact, you can notice that this is quite old compared to the age that we're showing for the emission that is coming just from the black hole itself. Yeah.
Would it be possible, I'm sorry.
Emir Ryan's actually made a seminar here 7 months ago where she talked about this percent of black hole in dwarf galaxy. And very interesting because we more or less found the same thing at her observations. Sorry.
Yeah, like related to the jet question that you posed, would it be possible for the jet to stop? Like to not be there because of the kick?
Yes.
Yeah.
So, I think so.
I'm just not sure how.
I don't know, I mean, I don't know if it is known, but at least I don't know how is the temporary connection between the feeding of the black hole with the jets, not yet production and life time, so.
Yeah.
I mean, I'm speaking as a non-expert here, just from my random knowledge. But if you have if the black hole moves fast, and I guess it gets a kick of several hundred kilometers per second in the simulation, if it moves fast, accretion will be extremely inefficient because then you end up on the Euler accretion and then the jet just will be off. That's my random knowledge that I can contribute. Yeah.
That's one of the problems we have actually, because if it's one of the complaints, if it's displayed, then it's not going to accrete and have feedback in an efficient way. So we think there is a bunch of black hole that we're not going to see because they don't detect it anymore.
Yeah. To counteract that argument though, if you have it depends probably on the galaxy type that falls in. Imagine a wet merger. So if the radially infalling galaxy has lots of gas, that gas may accrete around the black hole and create, and then you have the black hole moving, but with molecular gas, and then the feedback would be more efficient because then you could just move around and.
Well, then it's not just that, is it? Like it's also like the rotation and speed of the black hole. Like I'm not. I think it could also just like because you're not treating. Are you like it's just a point black hole? You're not considering that it's rotating. So I guess it doesn't matter whether the rotation is in the direction of the kick, or it's what I mean. Like I don't know. Maybe that be interesting as well.
Yeah. So from here, just to get back to what you were saying, if I show you the video again.
Sure.
Because so it doesn't want to go back. Okay. Here it is. So here you can see that it's a very simplified model, so we assume why is it not moving anymore? Okay. You see it's going in a random angle. So we just added a spherical geometry and so it's very simplified. We don't really look at what is happening really after the matter happens. Just the orbit of the black hole. It's really interesting.
More questions? No? Okay, if not, let's thank Alan again.